Our next speaker is, I hope that I pronounce his name correctly, Oliver Hoidn. Oliver did his PhD at the University of Washington in physics. He's now working on structural biology in Fred's group, which is part of Jana's department, as well as he's working on diffractive imaging and tychography. So the floor is yours.
All right. So I'm going to say a bit about the work that we're doing to handle the big amounts of data that we're expecting to come our way for X-ray microscopy at SLAC, especially LCLS. And what I'm going to focus on is the cost of analysis in lensless imaging experiments. So because X-ray optics are basically hard to build, if you want diffraction limited resolution, you have to go to these lensless techniques where you take out the optics. So you directly measure the diffraction on your detector of the coherent beam scattering off of your sample. And from the diffraction, you computationally reconstruct an image of the sample. And solving that diffraction to real space map, inverse map, it gives you significantly better resolution than lensed imaging, but because the computational recovery is expensive, this is really not a real-time technique. And so in X-ray microscopy, we have this kind of trade-off between speed and convenience versus resolution. So what I'm going to try to convince you of is that there's a way to break the dichotomy and get the best of both worlds in both speed and resolution, and that this can be something useful at LCLS. So here's a typical setup. You have an extended sample, and what you want to image is a function, a complex valued function of position that tells you how the amplitude and phase of a plane wave passing through your sample will change. And you move the beam to different positions on the sample, collect measurements of the diffracted intensity at each position. The diffracted intensity is just the amplitude of the wave field. So to get the full wave field in the sample plane, you need to solve what we call the phase problem. And that's helped along by redundancy in these real space overlaps between different measurements. And the way you do this typically is using something you can call a conventional iterative reconstruction algorithm. And basically these do alternating forward and back projections between real and reciprocal space, real and diffraction space. You have to do tricks basically to escape local minima in this non-convex optimization. And basically you have to run many iterations of this. And if you do the back of the envelope math, if you wanted to reconstruct 30,000 images per second, you would need something between 1 and 1,000 GPUs. And GPUs are expensive now, so that's really not convenient. So it was realized a while ago now that this could be a good use case for machine learning, because if you can train a neural net to fit the inverse map from diffraction images to real space image, to the real space image of your object, your sample, this will be intrinsically fast because you're just kind of running a single forward pass through the network at inference time instead of many iterations. And this was kind of demonstrated by Chirikar et al. Several years ago. The problem with the initial attempts were that you kind of get, so this is trained in a supervised fashion, you get physically inconsistent solutions, and also the resolution isn't very good. The other issue is that the model doesn't generalize well. So every time you move to a different sample, you need to, or a different type of sample, you basically need to retrain. So that made the approach not very useful initially, but a couple of years ago, we decided to take a stab at the problem. And what we found, just to kind of cut to the chase, is that if you incorporate physical priors into your model, you can get much better resolution. And you also generalize significantly better, such that the model doesn't have to be retrained. So how do you do this? Well, there's kind of popular thing in scientific ML, which is that if there's a known forward relationship between an intermediate quantity in your model and an observable, you can put that forward map into the model and then regularize the model towards physically consistent outputs by penalizing deviations between the output of the forward map from the model and the actual observable. And this works pretty well in this case because the intermediate quantity is the wave field. It's directly in the sample plane, is directly related to the image we want. And funny enough, for this diffracted imaging inverse problem, what works best is to not give the model any supervision in real space. Just train it in a purely self-supervised fashion and let the model figure out the inverse map with no direct instruction. So this works. Initially, I couldn't get this running on real data, so I had to make some adaptations, and then we finally started getting results on experimental data. Here are some reconstructions of an integrated circuit, biological sample, nanoparticles. That's from a preprint from our friends at APS. So this is a mix of APS and NSLS2 data, and we're also getting good results with LCLS data. So we think this is a good kind of foundation for tool for real-time lensless imaging at tychography beamlines. There are some kind of limitations. Probably the most severe one is that the neural net that we're using to learn the diffraction to real space inverse map doesn't scale well to high pixel resolution. So that means that we still can't compete with the resolution of conventional iterative reconstruction. So I'm looking at better architectures for that. There's also this kind of classic machine learning problem where you don't know when and how to trust the output of the model. So Ashwin is looking at uncertainty quantification using probabilistic ML approaches. So limitations, but also surprising benefits. We're finding out that it seems this approach is more robust to very sparse collection of your data, and that could be useful for samples that are damage sensitive. But I'm not going to talk about that. I'll just say a bit about the kind of modeling aspect. So there may be two paths to applying ML to this problem. One is if you want fast reconstruction, you use small models, and by putting in physical constraints, you can get kind of surprisingly good generalization from training on very small data sets. But if you wanted like the ultimate generalization, you would have to go to an architecture like the vision transformer that has just a higher model capacity. And that would be at the cost of speed at inference time. But it might be worth doing. And one kind of physical motivation for that is that if you think about the physics of diffraction, each point in your real space image depends on every single point in K-space in the diffraction. And CNNs only have this kind of local attention where they're looking at a patch, a small patch in the previous layer. That's not exactly what you want, but vision transformers do have this global attention property that might fit the problem better. So yeah, with that, I'll just wrap up and say all we're doing is solving one variation of a Fourier inverse problem, and our hope is that like anything that we discover, anything that we learn here might be useful to other imaging modalities and maybe even to inverse problem solving in general. So that's something that we're going to be looking out for in the next couple of years.